first introduce the speaker and then we ask the people to introduce, right? Okay. Hi everyone. It's a huge honor and pleasure to introduce. Yeah. It's on.
Yeah, I'm on too.
Do you hit? Okay. So, again, it's a really huge honor and pleasure to introduce Professor Kelly Killer, professor of. I wanted to say this by mind, but associate professor of in the Department of Civil and Environmental Engineering at Princeton. Got his PhD at University of North Carolina, Chapel Hill, in environmental sciences. Virginia. Oh, University of Virginia?
Yeah.
Okay.
Right? I think so.
Really?
Sounds right. Paul was there.
Where did I get that from?
That was Tom. Tom's
Oh,
Virginia
okay.
Tech.
Yeah. And this I'm really sure, director of the Princeton Eco Hydrology Lab. His research focuses on the interaction between land use and climate change and how this affects the resilience of drylands and also on isotope hydrology. Primary research sites are in Sub-Saharan Africa, and he's also a little bit of an inventor. He's working on development and deployment of cellular-based environmental sensors for improving agriculture and ecosystem functionings in developing countries, and has very interesting interdisciplinary and actionable research projects funded. Among these, the most recent one is an NSF grant on the impacts of agricultural decision making and adaptive management on food security. And previously a CNH grant on institutional dynamics in robust socio-ecological systems, adaptation to climate change in snow melt dependent agricultural systems, where he was a PI together with Elinor Ostrom. And so we have a norm here at CSync, that is that everybody introduces themselves, you know who you're speaking to. And so I will invite you to introduce.
Joe Marr, I'm a postdoc here, environmental economist, study mostly land use, energy, and ecosystem service issues.
Okay.
Welcome, Kelly. I'm Margaret Palmer, director. We're really happy to have you here. I look forward to chatting with you.
Thank you.
Hi, I'm Danny Weissman. I'm a master's student at University of Maryland, and I'm working on a project sea level rise and nutrient loading in the Chesapeake Bay.
Hi, I'm Lauren. I'm also a master's student at University of Maryland. Along with my master's degree in handle agricultural sciences,
I'm Phyllis Jewell, who we just met, and I'm a biogeochemist and at the University of Maryland Center for Environmental Science. And as you know, the focus of my research is on the effects of
Okay, so there we go. Now I don't have to shout as much. So I usually start talks this way. That little sphere there is all of the water on Earth, if it were collected in one spot. And that's all the water, including the oceans. And the way I get into the problems about agriculture and eco-hydrology is really just thinking about the scarcity of water in a planet that has a ton of water. Because most of that water is, if we were looking at that ball, 95% of that water is in the ocean. And if we figure out in the 3% of the water that's not in the ocean, where's that? It's mostly locked up in ice and snow and groundwater. And surface water is only 0.34% of that 3%. So it's a tiny fraction of the total water. If we think about the water that's being used in most subsistence agriculture, especially in dry lands, we have to think that most of that water is not the water that's in rivers and streams and lakes and wetlands. It's water that's in the soil, right? It's the rain that ends up in the soil and is available for evapotranspiration. So we call that the green water. That water has really two fates in dry lands. It either is transpired through leaves of vegetation, which goes to ecosystem productivity, or it's evaporated. And the point is, if we think about that blue-green water divide, most of the surface water is, in fact, in that blue water. So when we break it down, we find that the soil moisture is 14% of 0.34% of 3% of the water on Earth, which ends up being a tiny number. It's 0.001% of all the water on Earth is the main thing that drives all ecosystem productivity on the planet, right? We do a little bit of subsidy of that water with blue water in highly intensive agriculture, but this is a tiny fraction. If you want to try to calibrate that, the fraction of the budget of the US that goes into NSF is about 100 times larger, 200 times larger than the amount of water that's available for plants and ecosystems. So this is a tiny number. It's a highly variable number. The distribution of that soil moisture over the planet is not homogeneous at all, and there are large areas that have persistent deficits of water. And those are the areas I tend to study. So if we look at dry lands, they cover about 43% of the land area. They have a large portion of the global population, and that population is going to grow dramatically. Right? This is independent of the fact that the area of dry lands is probably going to change over the next 50 years. The number of people living in dry lands is also going up. And so if we look at where that might make the most difference in terms of the future of populations, we collapse pretty quickly on looking at Africa. If you look at the population growth curves on the right, you see that most of the future population growth that we're going to see over to 2100 is going to happen in Sub-Saharan Africa. And if you look at the availability of farmland and agricultural areas, they're really constrained to primarily being in Latin America and Sub-Saharan Africa. And that Latin America is basically the tropical rainforests, which are available for us to use as agriculture. And the Sub-Saharan African are the woodlands and savannas that dominate the dryland regions of Africa, where we're going to get about 3 billion more people. So I spent a lot of time working in my PhD, in my early career, looking at the eco-hydrology of natural landscapes in these sub-Saharan regions, really trying to understand how climate variability structures ecosystems and how the ecosystem function depends on that climate variability. But I think more recently and in the next few years, turning much more of that attention to understanding specifically dryland agricultural systems as probably the most important ecosystem to be studying in terms of understanding climate. So if you look at the kinds of models that we have and the expectations that we might be able to put together, this is some work from Lobel's group at Stanford, you see predictions of pretty substantial declines in yields across the board for a lot of different crops. This is maize. You can get similar things for soy, for beans. There's not a, the only consistent pattern is that we tend to see consistently expectation of lower yields. Even if we didn't have climate change happening, we already have a context of climate variability to deal with in a lot of these drylands. If you think about the main difference between tropical agriculture and temperate agriculture, it's the fact that the tropics tend to have much more highly variable climate regime. Rainfall from year to year is much more variable. So the coefficient of variability in annual rainfall is sometimes on the order of the average rainfall. So if you have 500 millimeters of rain, you might get something as low as 200 and something as high as 800, and that's not unusual. So in that context, you're seeing a lot of variability in crop yields. And so failure rates are fairly high. You're getting into the kind of 20%, so 1 in 5 years crop failure. that has real constraints in terms of thinking about capital investment. If you're trying to borrow money to maybe pay for some mechanized equipment and you have a 1 in 5 probability of a year of no income, it's very hard to kind of think about long-term investment and how you end up kind of capitalizing agriculture in a place where variability is so high. And you can see what the consequences of that are in terms of the coefficient of variability of maize yields and soy yields. In excess of 40% in a lot of regions. You can see the kind of belt of the northern Sahel, some areas of East Africa, and then a lot in the kind of central southern Africa region where you have a very high variability. So in the context of both change and variability, and I think one of the main drivers, we don't have time to unpack it, but one of the big things that's going to happen in Sub-Saharan Africa is that we're going to get more variability. So the change that we're going to observe is actually increasing variability from year to year. Right? And so it's not necessarily that we're going to see wholesale shifts in the rainfall regimes, but we're going to start to see characteristically fewer storms, larger storms that lead to interannual variability in rainfall that's going up. And in that context, we start thinking about how can we predict crop yields. And so this is just a simple kind of just diagnostic diagram showing the relationship between a very physically based process model of crop production, so DSAT, which is one of the probably 3 or 4 most common used crop models in almost commercially, but also certainly academically. And you're looking at a correlation between the model's process-based output and then NDVI-based what actually happened on the ground. So kind of a top-down versus bottom-up prediction, where the top-down is seeing what's happening in the landscape, and the bottom-up prediction is based on the climate drivers, but not actually constrained by the actual observations of NDVI. And you see there's some correlation there, but as you get into low productivity settings, so places where the DSAT model thinks the crop yields might be fairly low, we see a lot of variability. A lot of that variability is just from the simple fact that these models, to the extent that they're good at anything, they're good at predicting what crops do. And they have almost no information about what farmers are doing. And so when you get down to subsistence agriculture, a lot of the outcomes here, they're climate dependent, but they're the interaction between farmer decision making, climate dynamics, and crop productivity, right? And so trying to look at that residual, that huge spread of variability, and understand what's driving it is really at the heart of the research that we're starting to conduct. And if you need a simple quote that kind of sums up the challenge here, this one's not a bad place to start. That really what's driving these dynamics is stuff that's happening down at the household level, right? And so there's a need to really reach down to that level. People who, anyone here who's working on kind of smallholder agriculture, thinking about international agriculture, already kind of has internalized the importance of smallholder decision making at the farm scale. But how you connect that to environmental information and understanding the distribution of cropping patterns at that same scale is very difficult, right? So we have some mismatches in scales, which we'll get to in a minute. So the way we're thinking about this problem is really trying to frame it as an understanding of what's happening within a season. So a lot of what you may think about in terms of agriculture decision making could be kind of what a farmer might plant from year to year, or maybe in the margins where they're planting from year to year. But we're very interested in understanding what drives outcomes within the season. And this is kind of taking a piece of what you might think about in terms of a crop model, right? A process-based crop model is really looking at those seasonal dynamics to figure out the outcome. And we're trying to bring that same understanding of how important it is to track things through time within the season into the ideas of resilience and decision making at the kind of social dynamics scale, right? So the kind of processes that the farmers are doing in this kind of intra-seasonal dynamic. And so this is just kind of a conceptual diagram thinking about kind of relative adaptive capacity. What's the potential for different farmers to affect an outcome with respect to food security? So this could kind of be, you could have some T0, which is the beginning of a growing season, and at the end you have a harvest. By the time you get to harvest, obviously the cake has been baked. There's not a lot of anything anyone can do at that point. But the trajectories that you're following through time as an individual farmer depend highly on both the context of where you are in a kind of social environmental sense. Are you in some kind of highly connected integrated water project, or are you a very independent rain-fed farmer? And that kind of sets you at some initial condition. But then also the dynamics of the season itself, like how the season progresses in terms of this is a wet year or a dry year. And that's not something that you can often talk about at the seasonal scale. Is this a wet week or a dry week? And the week that it's dry versus wet matters. And so there's all this kinetics happening at the kind of micro scale inside the seasonal dynamics that really depend, they're, in this context, we're saying they're defining that relative adaptive capacity, but they also are defining the outcome, right? The ultimate thing that we're trying to predict. We'd like to have better traction on this so that we can do a better job of integrating across these distributions. You could think of any landscape as being some aggregation of a bunch of these different curves, right? And your average position in that distribution and the kind of underlying range of positions on that map are really your precursor for understanding what the food security outcome is going to be, right? It's not one trajectory, it's the distribution of these trajectories and how they're changing in time. And those can vary at the household scale within a community. So the main research questions that we're pursuing are really kind of these three things, all grounded on understanding these intra-seasonal dynamics. So how are these, going back to that last graph, how do these dynamics affect things like adaptive capacity? To what extent can we use mechanisms of intra-seasonal decision making to try to alleviate or to adapt to climate uncertainty? And to what extent is that happening now? So how do farmers make decisions, and how are they making those decisions in the context of uncertainty about the current season? What's going to happen next? How is climate informing their decision making or not? And then how can we develop data sets that improve the ability to model, predict, and enhance? So this is the synthesis part, and this is where I'm spending most of this talk, is really what can we do in terms of data? Just in case anyone's still kind of like, what am I talking about with intra versus inter-seasonal decision making? If you're thinking about the inter-seasonal, it's kind of like what and where to plant. Okay, and these are very important boundary conditions on the scope of agriculture. But within the season, there's a lot of decisions that are being made about timing of land operations, allocation of labor, social connections. What are you doing throughout the season that can be as important as what you did on that first day, right? And in many cases are. So it's hard to give a talk on any kind of these kind of couple dynamics without eventually getting into kind of a time-space diagram, because ultimately a lot of this is about when we have a problem we haven't worked on yet, we feel like there's an unknown and there's something to be done. It's usually because there's some mismatch between what we've done before and what we'd like to do next. If we think about what people need in terms of making decisions about subsistence agriculture, I would probably, to some extent, you could generalize this to almost any environmental decision making. At the very small scale, households maybe need daily information. This is kind of a farmer wanting to know what's going to happen this week. In the upper right corner, you've got the World Bank worrying about agriculture for all of Sub-Saharan Africa at the decadal scale, right? And things kind of run along this continuum, right? And that's just kind of a natural place to be. If you think about the way research gets done, it tends to kind of break out along that path. If we think about the kind of models we have, well, I come a lot from the physical modeling space, thinking about kind of climate models, but getting all the way down to kind of hydrological dynamics. Those models have a lot of skill across temporal domains. So we have models that are fairly effective at doing decadal things in terms of understanding the climate. But they can also get down to daily, weekly understanding of meteorology. But it's very hard to reach down into the spatial domain. So these models, even when they have the physics to do daily dynamics, it's hard to reach them down to something that gets to the scale of communities and households. And that's true of even something as simple as thinking like a weather model, right? Very hard to kind of talk to you about if it's going to rain at your house. Okay, so we know that that's a constraint. On the social modeling side, and the kind of decision making, so a lot of the work is done with agent-based models. Those agent-based models tend to be resolved at fairly fine resolutions. Often the individual is the agent, so these agents are being resolved at a household scale, or collections of agents are representing communities. But the kinetics of the agent-based models are often annual. Right? So there's some annual dynamics that's setting the agent behavior, and then that's what's changing through the model dynamics. So we have kind of a time step of a large time step at very fine resolutions, and then in the physical models we have a diversity of time steps, but they're at very coarse spatial resolutions in terms of their skill. So you can see that neither one of these really lines up on the lines that we'd like to have. And the argument is to make them work together, we really have to meet in the corner. Because the corner is where the interesting new physics are happening, right? It's that coupled interaction between the climate and the decision making that's happening at the individual scale, at the household scale, that really needs to be resolved to try to then walk up, in scale to these larger kind of, we need to know what's happening in the region over the season. That doesn't happen by pushing the models together across the boundary. It happens by going in the corner and then building out, right? So you have to kind of resolve the underlying physics at some scale, and then try to empirically aggregate up again. Okay, and so this is just kind of a standard kind of model scaling argument that it's better to have the kinetics at the small scale and then empirically derive the larger scale phenomenon rather than trying to jump straight to the empirical integration where you may be missing a lot of really important nonlinear dynamics that will matter when you go to implement the model. So why can't we do this now? The argument is that there's really three major obstacles. The first is that we don't have good information about what's happening at land use at the household scale. So highly resolved information about what's happening with agriculture on the ground in these regions. The decision-making dynamics aren't resolved at the time and space scales we need. And we also don't have the physical, and I'm putting this under the umbrella of eco-hydrological, but this is the coupled plant climate dynamics, right, which is essentially eco-hydrology. Here in this context, we're talking about agriculture. So we have three sets of data that we need. We have pieces of each of these. They're usually not collected in the same places at the same times in any coherent way. That makes synthesis and integration of these things exceedingly difficult. So let's start with the spatial agriculture problem. I'm going to walk through each of these, just give you the vignettes of how we're looking at these problems. So in agriculture, some places, if you look at the US Midwest, where is agriculture occurring? Well, everywhere, but also mapping this is pretty easy. If I want to know what's going on in Iowa, I can get that at very high resolution, fairly precisely, and people are kind of sorting that problem out. If I go into subsistence agriculture, the landscape mosaic looks much different. It's much more complicated. It's much more difficult to see what's happening on the ground. You can see these two images here. Where is the agriculture occurring in these images? How do we automate systems that can detect that and find these patterns reliably and consistently? Finding these patterns is hard, not just because the intensity of agriculture is lower in a lot of these regions, but also the scale is smaller. So the average farm holding sizes are very small in a lot of the developing world. In comparison to the kind of more temperate, developed agricultural settings, we're talking an order of magnitude lower, or 2 orders of magnitude in some cases, lower sizes of farms. Right? So these are small, hard to see things happening in landscapes that are highly heterogeneous. But they cover a lot of humanity and a lot of the agriculture that's happening on the planet. So what we've been trying to do is develop a system that we can allow us to automatically do this mapping. So really kind of build new tools that allow us to map agriculture in subsistence settings where it's hard to see what's happening. We don't have as clear a pattern, but we still need to understand the distribution of individual farms. It's not sufficient to know the fraction of agriculture happening. What's the size distribution of the farms that are in production versus ones that are out of production? How's that changing through time? The demographics of fields is just as important as the demographics of communities in terms of population, right? There's a lot of coupling between the way farms are operated and their sizes and the economic settings at which farming is happening that are driven by the distribution and location of fields. This is a hard problem in remote sensing. All right, so basically what we're asking is we're asking to find features, not to kind of map based on spectral data, but to actually find boundaries, perimeters, objects. All right, so this is semantic classification. It goes beyond kind of thinking about just a supervised kind of pixel-based classifier. And when you give a graduate student a quote like this, you get two outcomes. Either they get really excited or they drop out of the program. But so we've got some people working on this, but it's not, this is a problem that transcends agriculture. This is actually a huge challenge just in the remote sensing community. And so semantic classification, if that doesn't kind of like instantly kind of, if you don't grok what that means exactly, we're finding features in objects, right? We're finding features in objects and images. Something that we do very well, right, as people, something computers do very poorly, right? So teaching computers to see like humans is an ongoing project. And what we're looking at is solving the problem of looking, and this is even a little bit more structured. You can see that most of these images have pretty clear structure. When we look down at a landscape, we're even looking at a bigger mess, right? Other places of semantic classification, things like for biopsies, you know, identifying cells, detecting cancerous cells. There's a whole world of kind of trying to find pattern in biological data, and using semantic classification is doing that. So we've been doing some of this work in South Africa, mostly because we have excellent data on land cover maps. So the South African government paid to have all of their land cover data mapped. So not just is this agriculture or not, but actually field boundaries. So we have 30-meter resolution field boundaries for the whole country. That allows us to build a classification scheme on top of that to see how well we can do. right? So it gives us a nice set of training data. The kind of images we're working with look like these. So this is two, an off-season and a growing season images. So you can see, obviously, there's differences in images through time that are driven by seasonality. Some of that seasonality is related to the agricultural productivity. So there's actually information that you get from looking at multi-temporal data. And that shouldn't be very surprising. Turns out to be very important to get this right. You digitize that training data into a field map. So this is now a binary classifier. So we're looking at ones and zeros, where 1 is agriculture, 0 is not. We want a computer algorithm that will replicate that 1-0 behavior. The features we're using, not going to talk too much about these, but it's these quasi-exhaustive features. So it's a bunch of very simple features, not complicated patterns, but hundreds of thousands of different features. So the algorithm just exhaustively creates different types of shapes and looks at the boundaries and differences in the values of the pixels, at the image scale pixels in those features, and then runs a classifier based on the information it's getting out of those, right? And we're giving it some data to train on, where it has 1s and 0s and it knows what the 1s and 0s are, and then it's using arbitrary features. This is an example of just random patches. You can do differences of square patches. So what's this pixel look like versus the pixels around it? That one pixel, of course, you're moving that pixel over the entire image domain. So you're doing this, again, millions of times per image. You can look at differences between channels. Right? So this is getting at things like NDVI or something where you're looking at the difference in greenness and redness. So you can look at that, again, across features. We do not prescribe a feature set. We let the classifier build a feature set. How does it build the feature set? It develops a random forest. So more or less all options are on the table, and you start going down into these classifiers, and you start finding the features that are discriminating well between the 1s and 0s. Okay? You do that with all the features over all the images you have, and you eventually build a system that says if you're familiar with neural networks, this is kind of like a neural network in the sense that you build a kind of weighting scheme across your classifier to figure out what information is actually being provided. At the end of the day, what you're trying to do is kind of maximize this receiver operating characteristic curve, where your true positive rate is, both of these go from 0 to 1. So you want to be in this upper corner. An upper corner would be your true positive rate is always 1 and your false positive rate is 0. Right? So a best ROC curve is actually a square wave here with just 1 point here. If you're on this line, that means that, let's say the true positive rate at a location, some pixel is 0.5, and your false positive rate is also 0.5. That means you have no precision. Right? It's just as likely that you're wrong as you're right. And this line here is kind of the line of no discrimination. If you're below this line, somehow you're doing worse than random. Right? So you don't want to be there. Everybody wants to be above the line. You can see that the area under the curve here varies between a pure random process would be about 0.5 all the way up to 1. Right? So the area under the curve becomes kind of an integration of your ability to get both the sensitivity, which is how well you get true positives, and then 1 minus specificity, which is the false positive rate. So it's the ability to think 1 minus specificity, false positive is just the inverse of the true-false system. But let's not get into that whole the decision kind of confusion matrix. But the bottom line is we want curves that kind of get as far up into this range as we can. These are the curves that we get from our imagery. We see still variability between different images. Each one of these is an image result. But well above the curve, and you look at the AUC numbers, you see exactly kind of what you might expect to see. You do best on things like center pivot, right? But we're actually really happy we're not losing a lot of precision when we get in subsistence agriculture. Okay, so we have an algorithm that's really good at things that are really easy, but also very good at things that are very hard. Okay, and that's kind of a fair compromise in the world of remote sensing. We, of course, like that all these numbers be equally high and at 1, but if you think of the kind of center pivot as like the best possible scenario, like we probably won't ever get a classifier higher than that. We're happy that our fall off going down to the subsistence agriculture is in the 5% range. If you look at the kind of results we get, so this is an image, obviously growing season, greener. This is the off season. These are hand digitized labels, and this is the posterior probability, which is a number between 0 and 1 that the classifier said it's how much it thinks that this value should be a 1. Okay, does that make sense, right? So it's saying the probability, and the reds are 1s and the blues are 0s. So if it has a very low probability of being a 1, it's the zeros, right? And so you set a threshold here, and you kind of push everybody into 1 or 0. And the idea is that we're getting pretty good discrimination. We're able to pick up even fallow fields amidst the active fields. You can see how the precision, the kind of certainty drops as you get into subsistence agriculture. This is a much harder mosaic to see. You've got problems of like, fields aren't even contiguous. And just another example, again, very easy to do the center pivot commercial ag, but still, again, finding fields against a relatively difficult mosaic here. Nicely also generally avoiding the detection of roads, which is hard for these classifiers because we end up finding edges. It's really hard to avoid finding roads. That actually happens when you do the multi-season stuff. Right? Without the multi-season, you get fields and roads. But it can tell when it does its algorithms that this is too consistent to be an agricultural setting. So if you want more of this, we have a preprint out. I'm happy to circulate. Stephanie DeBass has been doing this stuff. She's easy to find. And we're really excited about it. We'd love to think about trying in new settings. This classifier is not designed for Sub-Saharan Africa. We just implemented it there because it is got all of the kinds of agriculture we'd like to solve. So if that's kind of figuring out where agriculture is occurring, we still have two big problems. One is, what are people doing in fields intra-seasonally? And the other one is, what is the environment doing in those fields, and how is it interacting with people? If we think about the way we characterize agricultural decision-making, a lot of that has been done traditionally through kind of pre- and post-harvest surveys. What are you planning to do? Come back 8 months later, what happened? These provide snapshots, annual time scale snapshots. In some cases, they've been run for decades. In some cases, they're very kind of haphazard, and you get 5 years, and then it drops. Very hard to get good longitudinal data. It's hard to know if you're talking to the same farmers from year to year. So there's a lot of this ends up getting aggregated to community scale or higher, usually kind of provincial even scales, because of uncertainty about the kind of ability to track decision making through time at the household scale. And of course, there's super expensive enumerators, driving around, trying to find farmers, trying to get them to sit down for an hour or two and do a survey. There's a lot of logistical constraints that actually make this difficult. Like I was saying, what you get from this is the ability to do things at kind of the province scale. So here's a map of food security by the FAOSTAT group out at UC Santa Barbara. You're seeing a map here of districts in Kenya. So fairly coarse scale resolution. Obviously, this is being driven by smaller scale information that's feeding up into that. But the necessity of aggregating to larger scale is really driven by kind of inconsistency in sampling in terms of knowing who's responding to these surveys through time. Okay. What is a problem with this? I kind of alluded to this earlier when I made the argument that we need these small-scale kinetics, but there are kind of nonlinearities and interactions between terms that require us to resolve these at the small scale, because if we try to empirically relate them at the larger scale, we'll miss those dynamics. Okay, so this is kind of a Jensen inequality thing where like the average of the function is not the function of the average. We have to get down to the small scale and understand what's happening there, and then we can average up. An example of this from our own data, this is some survey results that we did across southern province of Zambia. So you're looking at a scale here of maybe 130, 150 kilometers. Some cases, farmers that are neighbors, did you or did you not experience drought or kind of food insecurity driven by drought? A lot of variability. There's not consistency across this data set. It's not like it was all down here or all up there. There can be very distinct outcomes at very small spatial scales. This is driven by the complex interaction between what's happening at the field scale in terms of farmer management and the climate. And so all these variables, topographic, precipitation, farm management, are happening at very local scales. Anybody who's gone out and done these surveys, there's a logistical burden to doing that. Huge cost to the farmers in terms of time and effort. Huge cost to the projects in terms of time and effort. Right? A lot of man hours are spent filling in forms. Maybe you can automate that with an iPad or whatever. But the bottom line is this questionnaire survey system is brittle with respect to kind of scaling up and implementing it through time consistently. So what do we want to do? We want to know what farmers planted, where they plant, when they plant, how they manage for many farms matched to real-time ecological data. So we want this whole stack. And if we have it, we think then we'll be in a place to say something meaningful, something meaningfully new about what's going on in these dynamics. And so the way into that for us has been cell phones. Okay, so what we're doing is we're enrolling farmers in cell phone-based surveys. What it looks like is something like this. So the farmer's getting a weekly survey that they're responding to. It's a series of simple yes or no questions, sometimes categorical, 1, 2, or 3, depending on, like, did you plant this, this, or this. The flow that the farmer goes through is dependent on their answers. It's engaging in the sense that we're actually, connecting to the individual, right? Usually the grad student is the one running the survey, so it says, hi, it's Jacob, just checking in on how your farm's doing, right? So there's a lot of kind of connection here. And this is a natural interaction setting. Like, this is just a natural thing that farmers are used to doing, texting. And we get response rates in the order 80% or higher from these kinds of surveys. The flows are programmed kind of offline, right? We're doing this this is the pre-flight, right? And so all the standard kind of human subject stuff is happening in the survey, right? So this is the instrument. But the instrument is a dynamic thing that can change based on the farmer within the survey, or even the survey can change over time, right? So we have a lot of plasticity in what we do, but we know what we did, so we can replicate that, right? So we get kind of like scale in terms of asking people lots of different kinds of things, while at the same time not getting into this kind of problem where we get disparate data, right? Because we can be consistent in how we think about changing things or kind of reaching into new questions. And so again, like a very nice kind of script that's, kind of the the kind of IT helpline kind of thing, right? It's like, hey, they know me, I guess, and you feel like this is easy. I'm interacting with almost a human, but not. And we are able to get a lot of information. So we kind of move from a planting to growing season to harvest season flow right now. We're able to insert questions that get into new dynamics as we go. Things like how tall is your maize? This turns out to be a hard question to ask people. So when we enroll communities, they get like a meter stick, right? And so that becomes kind of like the meter stick. So in the survey, it's like take your meter stick and put it up against and see like where is it relative to the crop height. And so some of the observations we know are going to kind of have less precision than we would like to have. But at the same time, we're getting kind of a central limit theorem phenomenon that's going on where we're getting a lot more information than we would otherwise have. So just some examples of what this data looks like, just really raw stuff. This is a series of communities on the kind of north slope of Mount Kenya where we enrolled last spring, looking during the maize growing season. And I find this data set fascinating even just because it's so raw. This is farmer weekly expectations of the amount of maize harvest they're going to have at the end of the season, starting at the beginning of the season by week. You see the optimists, you see the pessimists, you see the people with a lot of upside surprise, and where's the poor guy? There was one guy that was like started high and just crashed out. I don't see it now. But one thing to take from this is that the beginning range we had was about 100 to, this guy is about 10. So a range of about 90. The actual outcome itself is still hugely variable. All right, so it's not like everybody converged. This is the actual yields at the end, right? And so that diversity within the community is crucial. It's understanding, like, if we just had one number from this, we'd have a much poorer idea what's going on. And trying to figure out how these things happen through time and what drove these expectations down or up, and why some farmers are just not yielding. I mean, there are some size-dependent things in here, but these are fairly similar-sized farms, so we're not looking at like wild variation in terms of like how much land they're cropping. So we're looking at variation in outcomes that are driven by the interaction between what the farmer's doing and what was happening on their field in terms of climate. So the climate piece is the last wrinkle, and so this is where I'll close today. And really, this was my entry point into this problem, right? So this is how I kind of started working in agriculture and started saying, well, what kind of data do we need to do better models of crop productivity? looking at what data is out there. This is a nice meta-analysis from 2012. Environmental data sources used in agricultural research studies, dominated by weather station data. This is the CREW data set, so the East Anglia gridded global climate data set. And you see a long tail of different people's favorite kind of agricultural, basic climate forcing data sets down here. But weather stations dominate what we use to understand agriculture, which nobody should be too surprised about. This graph's a little more worrisome, showing the number of available meteorological stations by region. Here's South Asia and East and West Africa I've highlighted over time. These curves are going in the wrong direction, right? Massive declines in the availability of this data. Some of these things can be explained by, like, this is India stopping the kind of routine publication of weather data. A lot of these decisions to kind of scale down, it's not that the stations are necessarily going dark with respect to, like, no one's collecting the data. It's not getting disseminated. A lot of that's being driven by kind of cost-based analysis of government services, kind of an argument that, like, hey, your data is profitable, you should be selling it. That leads it to kind of getting balkanized. And you can imagine, like, the way the US air traffic control system would work, or how our weather system would work if you had to pay for weather data. Right? I mean, we have a weather channel. We have a whole cable company built on free weather data, and we're kind of making data privatized in the developing world, which is a huge constraint on improving our understanding of what's happening with respect to climate there. So that's kind of an advocate for, like, please don't tell governments to sell their data. They get much more value from it by giving it away and letting people build services on top. But in the meantime, there's an opportunity to collect a new set of data. And to some extent, weather data is not exactly what we need. We want weather data and hydrological data, and we want it in fields. Right? It's not enough just to know what the temperature, humidity is. What's the soil moisture? How much did it rain? And in a field where we have a farmer who's giving us information about their decision making. So we really do need to couple these things. So even if we had all that station data, it would be a start, but it wouldn't be where we want to end up. Right? That station data to me is like the pre and post harvest survey data. Right? It's a great historical archive of information, but it's not exactly what we need. So what are we trying to do? Well, we're going to kind of leapfrog environmental sensing and build something that will work and do what we need it to do instead of kind of like what environmental sensing companies want or think that we need it to do. And what we need is something that's ubiquitous, cheap, and kind of open, right? And that kind of cuts against the basic business model of most environmental sensing companies, which want things that are very kind of selective, proprietary, expensive, and closed. So we're pushing the other direction. So this is kind of like the PC revolution against mainframe computing, right? Future is PC. This was the future now. So how can we do this? Well, ubiquitous is that was taken care of for us over the last 15 years. Cell phones are everywhere. Cell networks are everywhere. We have a robust global information network that we can just build something on top of. 10 years ago, building something on top of a robust global information network was very difficult. There were about 3 companies that could do that. Now, any of you can do that, right? You just order a couple parts. You go online, go to the maker store, get your SIM card, plug it in, and you've got a globally connected device, right? So the cheapness of this is driven by the ubiquity of smartphones and things like that, which have totally transformed mobile computing and made microcontrollers as cheap as any electronics thing that you could, I mean, right? They're putting them in toasters and stuff, right? It's getting out of control. But this provides an opportunity. And then over here, and this is the most recent thing, is the development of kind of distributed computing systems themselves, right? So open computing platforms, things like Heroku, platform as a service, so that you don't have to run your own backend. You don't have to build and engineer your own IT. You can just sit inside the same things that all the Silicon Valley startups are using to make their social apps, right? Except you can do that with an environmental data collection app. So this was kind of created passively, and it's just sitting there, and the idea is let's exploit that because it's a huge opportunity. This post-smartphone era that we're in is really as transformative as like the post-transistor era. It's like a phase change in the way we think about electronics and communication. So what we did about 3 years ago now is we started a lab, very creatively named it Princeton University Low-Cost Institute of the Army. Turns out Pulse is like, there's like 8 pulses at Princeton because PU is Princeton University. So yeah, all right. Well, anyway, so That doesn't matter because that was just a kind of front so that we could teach some courses, get some undergrads who maybe knew how to do this stuff better than we did, get them to help us develop these things. So we started a company about 2 years later, again, like kind of with some undergrads that had been in our classes. This is the kind of product we have right now. Completely self-contained, low-cost piece of hardware that's measuring all the environmental variables, has a plug-in for soil moisture. It's doing rainfall inside the sensor. It's got a disdrometer, an acoustic disdrometer, so it's not, there's no moving parts. It's got one button on it. You press the button, you're deployed online. It's got a GPS in it, so it knows where it is. All these things, I mean, it's not smarter than your phone. I mean, there's more sensors in this room probably than I've deployed in my life, and they're all in your pockets, right? But they were just trying to get that technology into the field. This is kind of like when you get into our app, you can see this. I just clipped this morning. So, you know, these are some sites. We were deploying these, so they don't yet have their final locations. These don't have GPS, so they get their location from a cell tower. And when when we address match on a cell tower location, the address is unknown. But you can see we're able to kind of get the data online. They report every 6 hours. So if you time it right, you're in there right as they're coming in. You can go into a notebook, look at the data. All this is downloadable, very easy. But even more important than just getting at the data is the whole thing's built on a back end that allows you to just grab the data through an API. So if you can just build a client. So if you want to get your data from MATLAB or R or Python or just at the web browser, you just build a client, you have an API key, you get your data. Because this is all done in a modern database, you can do queries like this query down here. It looks a little wordy, but clients don't care. Like, you know, you may not want to type that every time, but for a computer, it doesn't matter. But you can search by location. So it'll give you like whatever data is near a point arbitrarily, right? So this is kind of where we think we have an opportunity. Marry data like this with this kind of human decision-making data. And that allows us to get into this corner, technologically reach down into this otherwise difficult place to be through the use of a cell phone-based communication system for the environment and one based for the social dynamics, right? And by coupling these, you know, everyone talks about coupled system models. We're really much more interested in coupled system measurements. It's probably better to have a measurement before you build the model. Maybe. Opinions vary about that. So this is the idea. And just this fanatical co-location integration, you know, if we're collecting data in a field, we have information about that farmer, right? Not, oh, we've got some environmental data from a place 20 kilometers away. Let's just try to somehow munge these together, right? The idea is these dynamics are happening at scales that matter, and that co-location is integral to getting this right. So the whole thing kind of up here is our ultimate goal of understanding these kinds of adaptive capacities. But the middle layer here, the kind of middleware that makes this work, is the combination of, this is an older version of what these pods look like. That was kind of the beer can model. It's evolved. Coupling these new sensing technologies that kind of sit between what we have in terms of larger scale data sets, kind of maybe traditional data sets we have in terms of climate or the harvest surveys and remote sense data, and this kind of highly resolved individual base. And this is the piece that kind of glues that together, right? The bridge between these two. So in 5 years, this is where we want to be. About 15,000 farmers in Zambia and Kenya, about 1,000 of these pods out. Even 1,000 pods is about a $500,000 investment, so it's not a small amount of money, but it's possible. And then that data is going into things like forecast models and producing tools and products, but also, I think, science. I mean, like the bottom line is we want science out of this, right? I mean, people are going to graduate with PhDs and we're going to publish articles. Yeah, there's a great outcome here in terms of understanding food security, but I think at the bottom line is just the availability of this data is going to unearth a bunch of really interesting dynamics, and a bunch of interesting questions are going to fall out of those dynamics. And to me, that's the most exciting piece, right? A new data set is an opportunity for new understanding, and so we want to build a big new data set. Okay, so that's about it for me today. This is an NSF-supported project, Water Sustainability and Climate. We're in year 1, but we have some other projects, and this is all kind of leveraged on the work of a bunch of people at Princeton and Indiana graduate students at the top that are doing all the really hard work. I showed you Stephanie's stuff. Drew's been involved in the sensors. Paul McCord's been helping on developing the text-based SMS surveys. And then here's my kind of advertising pitch. There's a lot of students in the room. We're looking for students and postdocs. We would, if this sounds exciting to you, that's exciting to us. And so we'd like to have you out in the field on the team. Okay, so I'll just close there. If there's any questions, I'll be happy to take them. Thank you.